So in this class we will begin with metal halide clusters. Metal halide clusters. In the last class we have completed metal carbonyl clusters. Now if we just look at the transition elements, early and later transition metals or transition elements, early transition elements will have less number of electrons in it, later transition elements will have more number of electrons. So we say early transition elements are less basic, later transition elements are more basic. So if at all later transition metals has to choose to form any cluster, right? If at all they want to choose any cluster, most of the times they will be forming carbonyl clusters. Okay, they are ready to form carbonyl clusters. What is the reason for that? Because these are more basic. Suppose if a metal is combining with a ligand, metal will have more number of electrons, and that more number of electrons can be given to the ligand. So mostly they are ready to form carbonyl clusters. But when I come towards early transition metals which are less basic, suppose if at all they combine with a ligand, the number of electrons that are present in this metal are already less. Okay, so if at all it is trying to combine with carbonyl, it cannot give electrons back. Back donation is very, very difficult. So usually they do not form metal carbonyls. Usually, we don't say that they do not form completely, but the tendency is less. We have seen scandium do not form carbonyl. Titanium also does not form carbonyl until and unless I give two more excess electrons. TiCO6 was not there, but TiCO6 2- was existing. TiCO7 was not there, but TiCO6 2- was existing because the metal is becoming more basic. Okay. So what is that we have to conclude is early transition metals, they have less number of electrons, so they cannot combine with ligands like pi acids. But if at all I can give more number of electrons, suppose if I am choosing a ligand which can double donate, then is the metal ready to form a cluster? Yes, then the metal is ready to form a cluster. So if a ligand is able to form a sigma, if the ligand is able to form a pi, more number of electron density is coming towards the metal, stability of the metal and the ligand cluster will be more. Okay, so this can happen with pi bases. This can happen with pi bases. Okay, I'm just repeating this point. Whenever the metal is less basic, it is not ready to form a metal-metal bond because there is less number of electron density, it cannot easily form metal-metal bond. But if at all a metal is becoming more basic, if this metal is becoming more basic, then they can easily participate in a metal-metal bond, then the cluster stability will increase. So if I choose a pi acid, then it will be accepting electron density from the metal, metal become less basic, therefore cluster forming tendency drops. But if at all the ligand, it is a pi base, then it will double donate. Since it is double donating, the metal to metal bond stability will increase. So the conclusion is early transition metals prefer to form halide clusters, whereas later transition elements will prefer to form carbonyl clusters. Why are they preferring halide clusters? Because halides are pi bases. They double donate. Since they are double donating, metal becomes more basic and they can easily participate in the cluster formation. Okay, so just take down a statement. Early transition elements have less number of electrons. Early transition elements have less number of electrons. Therefore, to attain stability, Therefore, to attain stability of a cluster, to attain stability of a cluster, to attain stability of a cluster, they prefer to combine with, they prefer to combine with halides. They prefer to combine with halides because halides are pi bases. Halides are pi bases. Halides are pi bases. Okay. Next point. Coming towards early transition elements and later transition elements, to which metal clusters I can apply 18 electron rule? Usually for early transition metals, can I apply 18 electron rule? Generally not. Generally not. What is the reason? Because these are less basic, or instead of saying less basic, the number of electrons present in the metal are less. The number of electrons present in the metal are more. So very often they obey 18 electron rule, but most often the early transition elements do not obey 18 electron rule. Why can't they obey? Because the number of electrons present in them are already less. Since the number of electrons are less, they generally do not obey 18 electron rule. So never apply 18 electron rule for halide clusters. Okay? Because most of them, they do not obey 18 electron rule. Write down that point also. Halide clusters do not obey 18 electron rule. Halide clusters do not obey 18 electron rule. Therefore, to calculate the number of metal-metal bonds, 18 electron rule should not be applied. 18 electron rule should not be applied. So don't apply 18 electron rule. Then how should you go? If I ask you how many metal-metal bonds are present in a given cluster, halide cluster, how do you calculate? Let me take an example of Re2Cl8 2-. If I ask you how many metal-metal bonds are present in it, simply what you have to do is calculate the oxidation state of the metal. So what is the oxidation state of the metal? Altogether there are 8 negative charges, 2 are gone, therefore 6, therefore this should be 6 positives. 6 positives over 2 metals. So each metal is present in +3 oxidation state. Okay? If it is present in +3 oxidation state, how many electrons are present? 4 electrons. Because manganese, technetium, rhenium, there are 7 electrons. 3 are going for the oxidation state, 4 are remaining. In this case also there are 4 electrons. Don't try to pair them. Don't try to pair them because halides, they are weak ligands. In spectrochemical series we have seen halides are weak ligands. So the electrons do not get paired up. How many number of unpaired electrons are present? Those many number of metal-metal bonds are possible. Okay? So there are 4 unpaired electrons, 4 unpaired electrons, 2 electrons will pair up to give you a metal-metal bond. So altogether how many metal-metal bonds are present in rhenium? 4. Okay? We call it as a quadruple bond. So how do you calculate the number of metal-metal bonds? Means simply check the number of unpaired electrons present in the each metal. Then how many number of unpaired electrons are present? Those many number of metal-metal bonds will be forming. Okay? Write down that point. To calculate the number of metal-metal bonds, for a halide cluster, to calculate the number of metal-metal bonds for a halide cluster, comma, calculate the oxidation state, and find out and find out the number of unpaired electrons Next point. How many number of unpaired electrons are present? How many number of unpaired electrons are present? How many number of unpaired electrons are present? Those many number of metal-metal bonds, those many number of metal-metal bonds are possible. So how many d orbitals are present altogether? We know that there are 5 d orbitals. In the beginning classes of chemical bonding, if you could remember, I've given you all the possible combinations of sigma, pi and delta. Can you remember? Suppose if I take a sigma bond, how do a sigma bond form? I've given you a combination of S plus S, S plus PZ, S plus DZ square, or PZ plus PZ, PZ plus DZ square, or DZ square plus DZ square. All these are the combinations for the formation of a sigma bond. In a similar way, we have taken for pi, we have taken for delta. You just go through the previous classes. So if I take a DZ square has a symmetry to form a sigma bond. dxz and dyz has a symmetry to form a pi bond. dxy and dx square minus y square will have a symmetry to form a delta bond. Okay? So when I say dxy and dx square minus y square has a symmetry to form a delta bond, don't combine dxy and dx square minus y square. First of all, you take down that. Re to Cl 2 minus, just as an example. You take the number of metal-metal bonds. For the formation of a sigma bond, which orbitals can combine means dz square, it can combine with another dz square. Okay, you just note down this. The combinations for various bonds. So these two will combine, head-to-head overlap. This will give you sigma bond. dz square plus dz square will give you sigma bond, right? All these combinations we have done in the chemical bonding. You just go through that chemical bonding. dxy plus, sorry, next one is dxz plus dxz or dyz plus dyz. Don't combine dxz and dyz. This will give you what bond? It will give you pi bond. Sideway overlap. I'm just revising it. All these things we have done in chemical bonding you can go through. Sideway overlap will give you a pi bond. Suppose if I take this, what type of bond do you get? If I take that combination, this is like plus 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 plus, this is like plus plus minus minus, what do I get? This will give you sigma star. Now this is pi combination. This is a pi combination. Suppose if I want to get pi star, what type of combination is this? Sideway overlap, but it is plus to minus, minus to plus. Therefore, this will give you pi anti-bonding, pi star or pi anti-bonding. So sigma bonding, sigma anti-bonding combination, pi bonding, pi anti-bonding combination. And the last one, what is the other combination? Delta, very important one, dxy, another dxy, or dx square minus y square, another dx square minus y square. In this case, plus to plus, plus to plus, minus to minus, minus to minus. Eclipsed overlap. All four lobes of one orbital is overlapping with all four lobes of another orbital. This will give you delta. That is giving you delta bonding. Head-to-head overlap, sigma. Sideway overlap, where only two lobes are involved, it is pi. All four lobes are involved, it is delta. We call it as eclipsed overlap. Head-to-head overlap, sideway overlap. The last one is eclipsed overlap. This is for delta. Suppose if I want to take delta star, what are the combinations for delta star? This will be the combination for a delta star. Plus to minus, plus to minus, minus to plus, minus to plus. Okay, so this will be the combination for delta star or delta anti-bonding. Delta anti-bonding. They actually move away from one another. Here we draw it like this, but whenever they combine, this plus will move away, this plus will move away, these two minus will move away. So these are the various combinations for sigma, pi and delta combinations. Okay, so all bonds together. What point do you have to remember? A sigma bond will form due to a combination of dz square plus dz square. Pi bond will form due to a combination of dxz plus dxz or a dyz plus dyz. Delta bond will form due to a combination of xy and xy and x square minus y square and an x square minus y square. Cross will not happen. Cross means dxy cannot combine with dx square minus y square. Not possible. dxz cannot combine with dyz. For a pi bond, it is also not possible. So any such cross bonding is not possible. Suppose if I take a cluster, you are drawing it. Just imagine that I am taking a cluster. There is one metal-metal bond, two metal-metal bonds, three metal-metal bonds, and four metal-metal bonds. So what bonds will be existing between those two metals? First one will be sigma. Whenever there are two bonds, there will be sigma and a pi. Triple bond means sigma, pi, and a pi. Quadruple bond means and a delta. Okay, so sigma, sigma pi, sigma pi pi, sigma pi pi, delta. So wherever, if I give you a single metal-metal bond, just imagine that it is sigma. Let me just stretch it. Five bonds and six bonds. Sigma, pi, pi, delta, delta. Sigma, pi, pi, delta, delta, and phi. Sigma, pi, pi, delta, delta, and phi. Phi means f orbital is involved. All these are d orbitals, right? But wherever you get phi, it is involvement of f orbital. So whenever f orbital involves, phi bond will form. Phi. Six bonds is also possible. All these things are new for you. Single, double, triple is common. Quadruple, quintuple, sextuple, these are new bonds. But for our consideration, we will be going with quadruple. Quintuple and sextuple, they are not there, so don't bother about them. Quadruple we have to study. Write down a point. Depending on the number of metals, comma, halide clusters are classified into dinuclear, and polynuclear. Dinuclear and polynuclear. You just take down this simple classification. Dinuclear is further classified into all these things we have to discuss now. Dinuclear is further classified into four types. One is edge sharing by octahedra, phase sharing by octahedra. Third one is trigonal antiprismatic. And fourth one is tetragonal prismatic. In polynuclear we have trinuclear, tetranuclear, penta, hexa, and so on. but the most important ones are trinuclear and hexanuclear. Hexanuclear is octahedral clusters. Hexanuclear, directly we will be taking octahedral clusters. So I will directly give you some examples, try to work out. Write down a point. We'll begin with dinuclear clusters. First one, dinuclear clusters. First one, first point. These are the clusters. These are the clusters where the number of metal nuclei, these are the clusters where the number of metal nuclei are 2. The number of metal nuclei are 2. There are 4 important types. There are 4 important types. First one, edge sharing bioctahedra. Edge sharing bioctahedra. These are the clusters. These are the clusters where the two metals will have octahedral environment. The two metals will have octahedral environment, and both octahedra share a common edge. Both octahedra share a common edge. Both octahedra share a common edge. You just look at here. Around this metal, can you see an octahedral environment? Right? Where are the edges? Edges means the simple imaginary dotted lines which combine all the ligands to give you an octahedra. So all these dotted lines are the edges. Okay? You need not draw all these edges, but just for your understanding, this is one octahedral structure. Okay? In the same way, even for this you have a octahedral structure. This is an octahedra. This is another octahedra. Both octahedra are sharing a common edge. This is edge for this octahedra. This is an edge for this octahedra also. So both octahedra are sharing a common edge. It means both octahedra will have common ligands. So wherever if you find such a cluster, you call it as a edge sharing bioctahedra. There will be some metal-metal bonds in between. How many metal-metal bonds? That depends on how many number of unpaired electrons that are present. Okay? But this will be the basic structure of such a cluster. Okay? So just take down a simple octahedral diagram. You don't put all the dots, just you put octahedra, octahedra. Now with all these basics, I'll give you a simple example. Try to work out this structure. Zr2Cl6 Pr3 4. What type of questions appear from this? How many number of metal-metal bonds are present? What type of bond is present? How many halides are bridging? What is the oxidation state of the metal? All such questions can be expected. So just try to work out and try to give me the answer. Zr2Cl6 Pr3 4. Zirconium belong to group 4. I've given you a hint. It belongs to group 4. If zirconium belongs to group 4, how many electrons must be present in zirconium? 4 electrons. But what is the oxidation state of each zirconium? Phosphine is neutral. So each zirconium is present in +3 oxidation state. It means every zirconium has got one unpaired electron. When you have one unpaired electron in each zirconium, how many metal-metal bonds are possible? 1. Now can you draw the structure? Here itself I am putting this. Zirconium 3. Zirconium 3. This will have one unpaired electron, this will have one unpaired electron. Both will combine to give you metal-metal bond. This is the basic cluster. Now which ligands are present? We have chlorines and here will be phosphines. This is the structure of the cluster. Octahedra, they are sharing a common edge. Zr2Cl6 Pr3 4. Now just answer your questions. How many metal-metal bonds are present? One metal-metal bond is present. Is that metal-metal bond sigma, pi or delta? Sigma. Suppose if another question comes, which d orbital is involved in the metal-metal bonding of zirconium? It has to be dz square because there is only one sigma bond. So for a sigma bond, the combination is dz square plus dz square only. Next, how many halides that are bridging? Only 2 because it is edge sharing by octahedra. So 2 chlorines which are bridging. What is the oxidation state? Oxidation state is +3 for each metal. You have to remember this structure because maybe I can put chlorines here also. I can put phosphines here, but that is not occurring. So you have to put phosphines here only, chlorines here only. Put hafnium to Cl6 Pr3 4. Hafnium to Cl6 Pr3 4. How many metal-metal bonds? hafnium 2, Cl6, Pr3 4. How many metal-metal bonds? 1. Same. Because zirconium and hafnium, they are group members. So what combinations? Same. All these are same. Which ligands are bridging chlorines? How many? 2. Next one. Nb2Cl6 Pr3 4. Nb2Cl6 Pr3 4. How many metal-metal bonds? How many? 2. 2 metal-metal bonds. Nb2Cl6 Pr3 4, there will be 2 metal-metal bonds. Because niobium belong to which group? 5th group. Okay, vanadium, niobium, tantalum, it belongs to 5th group. Can you draw the structure? What difference do you see? What difference do you see? Here you can see chlorine, chlorine, but this is not chlorine and chlorine, it is Pr3 and Pr3. Chlorine is present here. Okay, so there is a clear-cut differentiation between the hafnium or zirconium cluster and your niobium cluster. What is that clear-cut differentiation? Structurally, the ligands are arranged differently. Okay, so this was a finding. First you draw the structure, I'll give you those points. That is the reason I always tell you should be knowing the examples. Without that, I just cannot predict where the Pr3s will be present or where the chlorines will be present. All such prediction is difficult. Finished? Write down a point. From the studies on metal halide clusters of group 4, 5 and 6, from the study on the metal halide clusters of group 4, 5 and 6, the following structural conclusions were made. The following structural conclusions were made. First one, in the case of group 4, with monodentate ligands, the structural configuration the structural configuration had a cis structure, cis hyphen cis structure, whereas for the halide clusters, of group 5 and 6, for the halide clusters of group 5 and 6, the configuration was called as cis trans structure. So now you can just look here once. This type of structure they call it as cis and cis. It is simply called it as cis and cis. Cis and cis means these are the bridging halides. With respect to this type of configuration they call it as cis and cis. Whereas in this case, one is like cis, another one is like a trans. Okay? So one you call it as a cis and cis, the another one is a cis and trans. This type of structure is possible only for fourth group. So suppose in the exam they give you zirconium or they may give you hafnium, this type of structure will only result. If at all they give you niobium or tantalum, that type of structure will result. Okay? Take down these two. This is for group 4. This is for group 5 and 6. One is for group 4 and the another one is for 5 and 6. This is about edge sharing by octahedra. I did not draw metal to metal bond. There will be metal bonds, only then I can call it as a cluster. You don't know what type of metal it is. So if it is a fourth group metal, then you can put one bond. If it is fifth group 2, sixth group 3, that depends. Therefore I did not put any metal bond. There will be a metal bond, only then I can call it as a cluster. Write a question. Predict the number of metal bonds. Predict the number of metal bonds and the structure for Nb2Cl6 DMPM twice. Nb2Cl6 DMPM twice. This is DMPM twice. Dimethyl phosphonomethane. Okay? Dimethyl phosphonomethane. If I replace these methyls with phenyl, suppose if I am replacing it with phenyl, what should I call the ligand as? Dimethyl phosphonomethane. In this case, diphenyl phosphonomethane. Okay? DPPM. Right? Suppose if I give you the ligand as, just imagine that I am giving you the ligand What is this ligand? Dimethyl phosphinoethane. Dimethyl phosphinoethane. Okay, it is DMPE. Suppose if I put phenyl instead of methyl, I put phenyl, diphenyl phosphinoethane. This will come in your what do you call, bioinorganic or some other clusters. DPPE, diphenyl phosphinoethane. DPPE is diphenyl phosphinoethane. What is the structure? Now here we have a different type of structure. It is a phosphine, it is neutral one. It is a neutral ligand. But it is a chelating ligand. Since it is a chelating ligand, it will come at this site. Previously phosphines, they were coming here. Phosphines were coming here. Now the phosphines are not coming here. They are bridging both the metals. That is the difference. You can compare the structures. In the previous case, we call it as cis-cis and cis-trans. This is neither cis-cis, it is neither cis-trans. All the chlorines are in one plane. All the chlorines are in one plane. And the phosphines are in the perpendicular plane. So it is a completely different structure. Is it an edge sharing by octahedra? Yes, this is the edge. Both octahedra are sharing a common edge. Whatever example that comes, you should be able to answer. Most of the times the question is about number of metal-metal bonds, because we don't know what is the structure. Mostly nobody can predict the structure. This is about edge sharing by octahedra. Next subheading, phase sharing by octahedra. Phase sharing by octahedra. Phase sharing by octahedra. These are the clusters. These are the clusters that share a common triangular face. That share a common triangular face. That share a common triangular face. Where each metal has octahedral environment. Each metal has octahedral environment, and the structure is also referred as confacial bioctahedra. Confacial bioctahedra. Confacial bioctahedra. Okay, so can you just draw the structure? Is it similar to which type of carbonyl cluster? we have done a carbonyl cluster Fe2CO9. It is similar to Fe2CO9. One of the best examples is W2Cl9 3 minus. Tell me how many metal-metal bonds are present. Between the two tungstens, how many metal-metal bonds are present? Each tungsten is present in which oxidation state? Tungsten is present in +3 oxidation state. 9 chlorines, 3 are going for the charge, 6 chlorines, 6 negatives means 6 positives. 6 positives over 2 metals, each metal has +3. So W3 means how many unpaired electrons? 3 unpaired electrons. In each tungsten there are 3 unpaired electrons. So 2 such tungstens combine to give you how many metal-metal bonds? 3. 1, 2 and 3. Therefore there should be a triple bond. If you have a triple bond, what are the different types of bonds that are formed? What are the different types of bonds? Sigma, pi, pi. What are the combinations? Which d orbitals are involved? This is a previous exam question, you can just go through. Which d orbitals are involved in the formation of sigma bond, or which d orbital is involved in the formation of pi bond? So sigma bond means dz square. 2 pi bonds, dxz is involved, dyz is also involved. Draw the structure. It has confacial bioctahedra structure. W2Cl9 2 minus. The number of examples will be very less from phase sharing, trigonal, prismatic and so on. You also write one more example. Nb2Cl6 Sr2 thrice. How many metal-metal bonds are present? Nb2Cl6 Sr2 thrice. Nb2Cl6 Sr2 thrice. Sr2 thrice. Sr2 is neutral. How many metal-metal bonds? What is the oxidation state of each niobium? It is +3. So +3 means how many unpaired electrons will be present? 2. Therefore there will be a double bond. So here we have an Sr2. The remaining are chlorines. This is the structure of Nb2Cl6 Sr2 thrice. We have seen that if these are forming 3 triangles, okay, in this triangle, suppose in this triangle, if this is 1, where is the corner? Corner is above, edge is below. Corner is above, edge is below. In this case, corner will be below, edge will be like above. Edge to corner. So these 2 triangles, they will be staggered to one another. These 2 triangles will be eclipsed to one another. First and third will be eclipsed. First and second, they will be staggered. So if this Sr2 is above, this Sr2 is like below. Hope you can understand. If this is your corner, this is upper corner. If this is your edge, this is your edge. Okay. So Sr2, they will not be like inline. If this Sr2 triangle is above, this will be below, this will be below. separately if I am just putting it, if this is one SR2, if this is another SR2, for the central triangle SR2 will be below. Okay? Or if I put the triangles opposite, then here if it is SR2, SR2, SR2. So either way. It means all SR2 are not in line. But anyway, that is not important. You never know what type of question CSIR will ask. Okay, coming to the next one. Edge sharing by octahedra is finished. Phase sharing by octahedra is finished. Third one, trigonal antiprismatic. Trigonal antiprismatic. The name itself tells two prisms are anti to one another. Trigonal antiprismatic. Write down a point. In this cluster, the two trigonal prisms, are found to be anti to one another. Are found to be anti to one another. Example, W2Cl6 or W2X6. W2Cl6 or W2X6. X could be some halide. How many metal-metal bonds are present? 3. So how are the two triangles? You can see the two triangles are anti to one another. Most important point, metal is not in the plane of your ligands. That is an important point to be noticed. I did not draw it like this. Can you see the difference? This is not the structure. Two triangles, they are staggered to one another. They are not like in plane with your metal. Metal is not in plane with your ligands. Metal is below, metal is above. So that it is like a prism. Can you say this is like a prism? The last one, the most important one, and most questions appear from that. So why did they call antiprismatic? Because two triangular units or two prism units, they are staggered to one another. They are not eclipsed, they are staggered to one another. Fourth one, the last one of dinuclear clusters. Tetragonal prismatic. Tetragonal prismatic. Tetragonal prismatic. Write a point. These are the dinuclear clusters These are the dinuclear clusters where the two metal units are eclipsed to one another. Two metal units are eclipsed to one another. Next point. Generally, a quadruple bond can be seen. Between the two combining metals. A quadruple bond can be seen between the two combining metals. One of the best examples is Re2Cl8 2 minus. Re2Cl8 2 minus. So just to take some data about Re2Cl8 2 minus. It is intensely colored. What is the color of it? Royal blue. It is intensely colored and the absorption occur at 7000 angstroms. There is a quadruple bond sigma, pi and delta. This is less important. This is very, very important. At least 3 to 4 questions have appeared in the previous CSIR exam questions just on this delta. Why is the color intensely blue? That is one more question. Why should it be intense? So to understand all these concepts, first I will come with some basics. How many valency orbitals are present for a transition element? How many? 9. So this we have discussed previously also. Write down. There are 9 valency orbitals for a transition element. These are look here once. We have 2 rheniums. Okay. If I am taking one rhenium, it has all the 9 valency orbitals. I take the second rhenium, it will also have 9 valency orbitals. But what is the structure we have drawn? Suppose if this is one rhenium, this is another rhenium. It is combining with how many ligands? Each rhenium is combining with 4 ligands. So what is the structure of this, or what is the geometry of this? It is a square plane. So this particular metal is combining with 4 chlorines to give you a square plane geometry. This particular metal is combining with 4 ligands to give you square plane geometry. But after they combine, it will not be a perfect square plane, it will be tetragonal. Because of quadruple bond, they come very much closer. Chlorines will repel, so it will be out of the plane. But just to understand, this is a square plane. This is also a square plane. If I say square plane geometry, which orbitals are involved in it? Square plane geometry, which orbitals are involved? S is involved. dsp2. Square plane means dsp2. px is involved. py is involved. pz is not involved in dsp2 hybridization. Then dx square minus y square. That is a very, very important point. Okay, the most important point. In dsp2 hybridization, which d orbital is involved? either dxy or dx square minus y square can be involved because it is in xy plane. But in this case, x square minus y square is only symmetrically matching with those ligands, therefore it is participating in bonding with the ligands. Yes? So from both metals, these are going for dsp2. Okay, they are gone. How many orbitals are left out? 1, 2, 3, 4, 5 orbitals are left out. dz square, they participate in sigma bonding. So dz square and dz square, they are participating in sigma. dxz and dxz, pi. dyz and dyz, pi. What is left out for delta? This is many times asked question. Which d orbital is involved in the delta bonding of rhenium to Cl8 2 minus? It is not dx square minus y square, it is dxy. Though both orbitals have same symmetry, both can form delta bond, but this is involved in bonding with the ligands, it is not available for metal-metal bond. So the only available bond is, the only available orbital is dxy. This is participating in delta. How many bonds you are getting? 1, 2, 3, 4. Therefore it is a quadruple bond. So which orbital do not participate in bonding? Pz. Okay, so just take down this. You are getting so many points from this. Which orbitals are participating in hybridization with the ligands means dsp2. Which d orbital? Dx square minus y square. Which p orbitals? Px and py. Pz is not participating. Pz is unparticipating. You can just note down a point after this. From each metal, S, Px, Py, dx square minus y square. From each metal S, Px, Py and dx square minus y square participate in hybridization with the ligands. Participate in hybridization with the ligands. This leaves dz square, dxz, dyz and dxy for the metal bond participation. Metal bond participation. Next, the two square plane units are joined by the two square plane units are joined by a quadruple bond. A quadruple bond. Due to this, the structure becomes tetragonal prismatic. Instead of being tetragonal prismatic, instead of being square prismatic, instead of being square prismatic. Instead of being square prismatic. So just for 1 minute you try to understand. These are the two units, right? Chlorine, 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 chlorine and chlorine. There is a quadruple bond, it means bond length will be very, very less. Forget about the back bonds. These two are back bonds, so just forget about it. This is also away from you, forget. This is also away from you, you forget. This is towards you, towards you, towards you and towards you. Chlorine is larger because it belongs to third period. Exactly below there is another chlorine, this is also larger. This is large and this is also large. So whenever there is a quadruple bond, they come so close to one another that the van der Waals radius is just going. There will be some van der Waals radius between these two and they are almost overlapping it. So due to that overlapping, repulsions will be there. Due to those repulsions, they don't want to come close to one another. This will go up, this will go down. So that it will not be in plane, this will be going up, this will be going down. So the resultant structure will be like this. The rhenium is not in plane with your chlorines. It is just like a prism. It is just like a prism. So for that reason you are calling it as tetragonal prismatic. You don't call it as a square prismatic. Did you get the point? You can draw this structure. In some books you will find this structure. This is also accepted. This is also accepted, but it is not correct. This is like a square plane, but due to quadruple bond, the chlorines exceed their van der Waals radius and due to repulsions they move away from one another. You will be getting this geometry. This is the right one. This is not the correct one. Rhenium should have which vacant orbital? This will be pz. This will be pz. So there is a vacant pz orbital which you need not draw. Just for your understanding I am giving you. Because later when we perform a reaction you will come to know what is the importance of that pz. Write down a point. The bond length of a quadruple bond, the bond length of a quadruple bond is very short, therefore the chlorines from the two square plane units, come very close to one another, where they exceed EXCEED, where they exceed van der Waals radius, This lead to repulsions. This lead to repulsions between the chlorines. Between the chlorines means chlorine of the above unit, chlorine of the below unit, not of the same unit. This leads to repulsions between the chlorines, due to which each square plane unit become prismatic. Next, on every rhenium there is a vacant p orbital. There is a vacant p orbital which is a pz. Try to get the answer. Re2Cl2 minus plus 4 acetates. What could be your product? Just try to draw the structure of your product. Take a minute of time. Re2Cl2 minus plus 4 acetates. I am giving you a hint. Each acetate is a bidentate ligand. You take it as a bidentate ligand. What is your product? It is a bidentate ligand. I will also give you another hint. All the acetates will enter into the coordination sphere. All the acetates will enter into the coordination sphere. What is your product? Re2, CS3, now this is your product. Look carefully about your product. If every acetate is a bidentate and if 4 acetates are entering into the coordination sphere, that should replace how many chlorines? 8 chlorines it has to replace because 4 acetates are entering. But how many chlorines are being replaced? Only 6 chlorines are being replaced. You are still getting 2 more chlorines. Where do those 2 chlorines go? Now you have PZ on each rhenium, so that chlorine will go onto that PZ. Okay? Did you get the importance of that PZ? Take down this reaction. So where do those chlorines add means? Those chlorines will be adding onto your PZ. Here you can simply draw as a square plane because oxygen is a smaller atom. Unlike chlorine, it is a smaller atom. Here is one chlorine, here is a second chlorine. Now where should you draw the acetates? In one of the classes I have told you, the acetate will not come like this, it will come like this. So it will be 1, 2 above rhenium, below rhenium, towards you. CS3 COO, away rhenium, I mean away to the rhenium. One more acetate. Towards you, away from you. This is the structure of your cluster. In one of the previous exams, they have asked what is the point group of Re2Cl2 minus. What is the symmetry point group of Re2Cl2 minus? What is the point group of this molecule? Symmetry point group? D4H. So this is D4H. This is also D4H. So are you able to imagine the structure? Acetates, 4 acetates, one above, one below. If you are finding difficulty, the same structure can be drawn in a different way. It is like you are looking from here. Okay? So in this case, this is chlorine, this is a chlorine, this is one acetate, this is a second acetate, third and fourth I am just putting it above. One, this is above. Are you able to see the red? This is one. So this is one acetate, this is one acetate, this is one, and this is one. Can you see? 1, 2, 3, 4. It is just like if this is one acetate, this is second, this is third, and this is fourth. So you have a C4 rotational axis, and there are two such units, therefore it belongs to D4H. So whichever is convenient for you, you can draw. The same one, if you are watching it from below or above, this is how it looks. Okay? Why is it intensely colored? What are the different types of transitions that can occur? We'll discuss after a short break. Because it has appeared in many exams. Just after 10 minutes, we'll continue. Okay, write down a point. The intense color of the dinuclear halide clusters, the intense color of dinuclear halide clusters can be explained on the basis of electronic transitions. On the basis of electronic transitions. On the basis of electronic transitions. Can you just look at the orbitals that are participating in metal-metal bonding? We have 5 d orbitals from each metal. So suppose if I am taking one metal here, another metal is also here. There are 5 d orbitals from that metal, 5 d orbitals from this metal. Altogether 10 d orbitals will participate. Out of which 5 will be bonding, 5 will be anti-bonding. Okay? But what we have seen is, this is one orbital which will participate in bonding with the ligand. So whenever I am removing dx square minus y square bonding, you should also remove dx square minus y square anti-bonding. So you just remove those orbitals from the molecular orbital diagram. Suppose if this is the energy scale. Within this energy scale, sigma is the least energy or sigma is the most stable one. Then will be your pi, then will be your delta, then is delta star, pi star and sigma star. Suppose if I want to write the G-rayed or un-G-rayed parity, what is the parity? In chemical bonding we have discussed all this parity. Sigma will have G-rayed, pi will have un-G-rayed, delta will have G-rayed, delta star un-G-rayed, pi star G-rayed and sigma star will have un-G-rayed. So in our electronic spectroscopy there is a basic. What is that basic? In the next unit we will be going for spectroscopy. So in that there is one selection rule. According to that selection rule, transitions having same parity are forbidden. Transitions occurring between the orbitals having same parity are forbidden. Whereas transitions occurring between the two different orbitals of different parity are allowed. So G-rayed to un-G-rayed or un-G-rayed to G-rayed is allowed. G-rayed to G-rayed, un-G-rayed to un-G-rayed is forbidden. Okay. So based on this we can predict the electronic transitions. Right. So altogether how many orbitals can participate in molecular orbital diagram means 10 orbitals can participate. But out of those 10 orbitals, 2 orbitals are participating in bonding with the ligands. So we just subtract them. How many are left out? We are only left out with 4 orbitals in each metal. So these 4 orbitals will participate in metal-metal bonding. These 4 orbitals are only now participating, where this will be sigma, pi, delta. This will be delta star, pi star, and this will be a sigma star. So this is our molecular orbital energy level diagram. This diagram you have to consider for all dinuclear halide clusters. Whatever may be the question that is asked in the exam, consider only this diagram, don't consider that diagram. Okay. Let it be the question related to Re2CH3 8 2 minus, or they may ask you MO2Cl8 4 minus. Whatever be the dihalide cluster, only follow this particular diagram. Okay. Now let us check why there is a intense transition. I have taken Re2Cl8 2 minus. How many electrons are present in each rhenium? How many electrons are present in each rhenium? 4 electrons are present altogether. So one rhenium is giving you 4 electron. Another rhenium is giving you 4 electron. Altogether 8 electrons. Where do those 8 electrons settle down? These 8 electrons will settle down into bonding orbitals. 1, 2, 3, 4, 5, 6, 7 and 8. Okay. What is the bond order? Number of bonding electrons minus number of antibonding electrons by 2. So bond order is 4. We got it. Bond order is 4. Next, suppose if I give you some energy, I'm just giving you some energy, there will be an electronic transition. This electronic transition will make this electron jump into delta star. So what type of electronic transition it is? The electronic transition is delta to delta star. What is the parity of delta? G-rayed. What is the parity of delta star? Un-G-rayed. G-rayed to un-G-rayed is allowed transition. Since it is an allowed transition, the intensity of transition will be very, very high. Probability is very high. Intensity is also very, very high. Therefore, Re2Cl8 2 minus is intensely royal blue colored. The simple reason is allowed electronic transition from delta to delta star, which is G-rayed to un-G-rayed. This is the reason. So whatever cluster that they give you, if you want to calculate the bond order, follow this MOUD. Or if you want to know whether there is an electronic transition which is intense or not, just put these orbitals, try to excite the electron. Okay. Now you just take down a point. Have you taken that one orbital must be excluded? No? Write down. From 5d orbitals, exclude dx square minus y square. From 5d orbitals, exclude dx square minus y square because it participates because it participates in bonding, with the ligands, with the ligands. The remaining orbitals make MAKE. The remaining orbitals make the MOED. MOED means molecular orbital energy level diagram. The remaining orbitals make the MOED. So first draw the right side portion. Then you remove the dx square minus y square. Once you remove, you will be left out only with 4 BMOs, 4 ABMOs. Then you write down the left side diagram, where you can also fill the electrons, write the parity, G-rad and G-rad. Some dinuclear clusters are intensely colored yellow, some are red colored, some are blue colored. The reasons are mainly delta to delta star. Also, the energy difference between delta to delta star is found to be less. You can also calculate the bond order. So what electronic transition is occurring in rhenium 2 cluster means? Answer is delta to delta star. It is an allowed transition. It is not a forbidden one. It is an allowed transition. Therefore, it is intensely colored. Write down a few points. The electronic transition that occur in this cluster, the electronic transition that occur in this cluster is delta to delta star, which is a Laporte allowed transition. Which is a Laporte allowed transition. We have two selection rules, out of which Laporte selection rule is one. So we call it as Laporte allowed transition. And hence intensity is very high. And hence intensity is very high. And hence intensity is very high. Next. The same MOED, MOED means molecular orbital energy level diagram. The same MOED can be applied, to calculate the bond orders, of similar dinuclear clusters, Now just calculate the bond orders of these clusters. Rhenium to CS3 8 taken 2 minus, CS3 is methyl. We have to take one negative charge for methyl. One negative charge for methyl. So how do you go about it? One example I am telling you. Rhenium to CS3 8 2 minus. There are 8 negative charges. Each methyl is taken as one negative charge. Each rhenium, I don't know what is the oxidation state, I am taking it as 2x. 2x minus 8 is equal to minus 2. So 2x equals 8 minus 2. 2x equals 6, x equal to 3. It means each rhenium is present in plus 3 oxidation state. So rhenium plus 3 is a D4 configurated. Each rhenium has how many electrons now? There are 4 electrons in each rhenium. Which MOED I am taking? This one I am considering. So altogether I have 4 electrons in one rhenium, 4 electrons in the another rhenium, 8 electrons. I am just adding those 8 electrons. What is the bond order? 4. So the bond order for rhenium cluster, methyl is also 4. Okay. You can put that bond order. If you want, you can just roughly draw this diagram. For molybdenum, can you calculate? How much molybdenum? Can anyone tell? MO2Cl8 4 minus. So 2x minus 8 is equal to minus 4. 2x equal to 4, x equal to 2. Molybdenum 2, it is also D4. Molybdenum 2 is a D4. So how many electrons are present in each molybdenum means 4 electrons. 4 plus 4, 8. So again the bond order will be how much? 4. So for molybdenum to Cl8 4 minus also the bond order is 4. Next molybdenum to acetate. It is again 4 because each acetate will carry minus 1 charge. So each molybdenum is present in plus 2 oxidation state for third cluster also. So the bond order is again 4. First, second, third, the bond order is 4. Fourth one. Can anyone? Fourth one. Rhodium to 4 plus. I don't know the oxidation state, so 2x is equal to plus 4, x is equal to 2. Right? How much is x? X is equal to 2. So each rhodium is present in plus 2 oxidation state, D7. How many such rhodiums are there? 2. So 7 plus 7, 14 electrons. Give me the bond order. Rhodium to 4 plus. When I tell rhodium to 4 plus means each rhodium is present in plus 2 oxidation state. Altogether there are 14 electrons. So where do you fill those 14 electrons? 1, 2, 3, 4, 5, 6, 7, 8. 8 are completed. 9, 10, 11, 12, 13, 14. Now what is the bond order? 8 minus 6 by 2. So the bond order is 1. How many electrons are present? 14 electron system. Though there are 14 electrons, the bond order is just 1. the bond order is just 1. So this particular bond order is called as electron rich single bond. It is called as electron rich single bond. I am just repeating this point. Suppose if I am giving you some dinuclear cluster, okay, just I have given you some dinuclear cluster. In this dinuclear cluster there are only 2 electrons from 2 metals. There are only 2 electrons. What will be the bond order? Bond order will be 1. There are only 2 electrons, bond order is 1. Here there are 14 electrons, the bond order is again 1. So this 2 electron giving rise to bond order 1 is called as electron poor system. This is called as electron rich system. So electron poor single bond, electron rich single bond. Okay. Whatever cluster they may give you, it is very easy. Simply calculate how many electrons are present in each metal, combine them, try to arrange them into the orbitals. That will give you the bond order. Write a point. Rhodium-2 4 plus, rhodium-2 4 plus has electron rich single bond, electron rich single bond. This table will help you to directly calculate the bond order. When do you get a bond order of 1? How many electron system? 2. For 1.5, 3, 2, 2.5, 3, 3.5. When do you get 4 bond order? When you have 8 electrons. Now just look once. Suppose if any dinuclear cluster has 14 electrons in it. Directly if you get 14 electrons, what will be the bond order? 1. 13 electrons, 1.5. 12 electrons, 2. So you can directly remember this. 2, 3, 4, 5, 6, 7, 8. 9, 10, 11, 12, 13 and 14. So previously we have given you rhodium-2 4 plus. How many electron system it is? 14 electron system. Since it is 14 electron system, bond order is 1. We have taken rhenium-2 Cl8 2 minus, rhenium-2 CS3 8 2 minus, or molybdenum-2 Cl8 4 minus, molybdenum-2 acetates 4. All these cases the bond order was found to be 4 because the number of electrons are 8. From this you can get one question. When we go to previous exam question discussion, you will come to know how important are these topics. So electron poor system or electron rich system, they have the same bond order. Finished? Write down a question. When Re2Cl8 2 minus, when Re2Cl8 2 minus react with excess of chlorine, it produces Re2Cl9 minus. It produces Re2Cl9 minus. What is the bond order? What is the bond order and structure of it? What is the bond order and structure of it? So what is the bond order? Nine. You are getting it as 4. Right. So each rhenium is present in +4 oxidation state. How many electrons will be present? 3. Rhenium +4 means it is 3. Each rhenium has 3 electrons. 2 rheniums, 6 electrons. What will be the bond order? Bond order will be 3. So the bond order for that cluster is 3. And what is the structure? Structure was found to be this. Where did you see this type of a cluster? W2 Cl9 3 minus. W2 Cl9 3 minus, Fe2 CO9, same structure, you are also finding it here, Re2 Cl9 minus. It is called as a confacial bioctahedra structure. So related questions can be asked. Simply have to calculate the oxidation state, find out how many electrons are present in each metal, sum them up, add them up, and just try to put it into the orbitals. Finished. Next subheading. Trinuclear halide clusters. Trinuclear halide clusters. Trinuclear halide clusters. The best examples are Re3X9. 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 Take another example, Re3Cl9. Re3Cl9. What is the oxidation state of each metal? Each metal is present in +3 oxidation state. It means how many electrons are present? 4 electrons. So how many metal-metal bonds are possible? 4. Single, double, triple, quadruple? Quadruple. Can you draw the structure? Try to draw it. Try to draw the structure. You got D4, so directly you put a quadruple bond. But how do you put a quadruple bond? There are 3 metals. There are 3 metals. Should I draw it like this? Can I draw it like this? No, because this is giving you 4, this is giving you 4, but this is having 4 plus 4, 8. This will go wrong. So these are trinuclear halide clusters, not dinuclear, trinuclear. So the structure will be put it like a triangle. In this triangle, each rhenium has 4 bonds. 1, 2, 3, and 4. For this rhenium, 1, 2, 3, and 4. For this rhenium also 1, 2, 3, 4. Next, how many chlorines are there? Altogether there are 9 chlorines. Out of these 9 chlorines, Okay, for these 9 chlorines, you just look. One chlorine, it is above, above, and above. So these 3 chlorines are above. Below, below, and below. So 3 chlorines are above, making a triangle. 3 chlorines are below, it is also making a triangle. Because the central core or the skeleton is a triangle. Exactly above and below there is another triangle of chlorines. One triangle, second triangle, and a third triangle. Altogether 6 chlorines are completed. We are left out with 3 more chlorines. These 3 chlorines will be doubly bridged. So one chlorine is doubly bridged, second chlorine is doubly bridged, third chlorine is doubly bridged. The remaining 3 chlorines are terminal, 3 chlorines are terminal. Okay. What is the point group of this structure? This was another previous exam question. These are like to the point. All clusters, whatever small topic we discuss, that will come in the exam. One triangle, another triangle, third triangle, or all eclipsed. D3H. Point group is D3H because the skeleton is triangular skeleton. Okay. The point group is D3H. The same Re3Cl9, can I write it like this? Re3Cl6 mu2Cl3. Can I write it in that way? Re2Cl6 mu2Cl taken thrice. It means out of 9 chlorines, 6 are terminal, the remaining 3 are doubly bridging or edge bridging. 3 chlorines are doubly bridging or edge bridging. Suppose if I ask you a question, for each metal, how many metal-metal bonds are present? For each metal, how many metal-metal bonds? 1, 2, 3, 4. For every metal, there are 4 metal-metal bonds. Between 2 metals, how many metal-metal bonds? 2. In the cluster, how many metal-metal bonds? In the cluster, 6. 2 plus 2 plus 2. So what question are they asking in the exam? Accordingly, you have to give the answer. Are they asking in the cluster? Are they asking between the metals? Or are they asking for the metal? Based on that, you have to give the answer. Okay? So just write down those points. The number of MM bonds, MM means metal-metal bonds. The number of metal-metal bonds for the cluster is 6 for the cluster is 6 comma between 2 metals it is 2. Between 2 metals it is 2. And for each rhenium, there are 4 metal-metal bonds. And for each rhenium, there are 4 metal-metal bonds. So overall cluster has 6. Between 2 rheniums are 2, but for each rhenium is 4. Finished? Completed? In your carbonyl cluster, suppose if I give you a bridging carbonyl and I'll also give you a terminal carbonyl, which one is stronger, which one is weaker? Suppose I just start heating. Whenever I start heating, which one will break at first? Bridging will break at first. Whereas in this case, the bridging halides are much more stronger than the terminal halides. Okay? How did we come to know? There is a reaction. In that reaction, this cluster, whenever it participates in a reaction, this can take up few more ligands. these clusters can take up few more ligands. It can add on to some more ligands also. That ligand could be a phosphine, that ligand could be anything else other than these chlorines and the bridging chlorines. An outside ligand can also come and attack. So it can also bind with another ligand. There is also some space for the rhenium. Okay. Now we have how many different types of ligands altogether in the cluster? What are the different types of ligands we have? We have L, we have bridging chlorine, and we have terminal chlorine. They have tested the lability order. All this reactivity is not needed, but they have tested the lability order. If I take such a cluster which is attached to some ligands, and if I put it into some other reaction, which ligand will come out first? What is the lability order? In that lability order, they got it as L. L means the added ligand, it will come out at first. After this will be your terminal ligand. CLT means terminal, you try to understand. Finally will be bridging chlorine. So bridging chlorine is found to be the strongest one. Okay. So whenever I participate this cluster, I put the cluster into some reaction mechanism. The first ligand that will be replaced is the one which is added later. First of all, this will go away. Later, terminal chlorine will break. Later, bridging chlorine will break. I'll put still harsh conditions. Then what will happen? Then the cluster will rupture, skeleton will rupture. Until that point, the triangular skeleton will remain intact. But whenever the conditions are becoming very drastic, only in such case metal-metal bonds will break. Okay, write down that point. Re3Cl9 can participate in reactions. Re3Cl9 can participate in reactions and can add up other ligands also, and can add up other ligands also. Next, when such a cluster further participates in reactions, the lability order is found to be, write down this lability order. The lability order is found to be L greater than terminal chlorine greater than bridging chlorine. That is your lability order. The lability order is found to be L greater than terminal chlorine greater than bridging chlorine. We have to discuss octahedral halide clusters, which will take some time. So just write down some questions. Finished? Now try to be as fast as possible. Okay? Write the question. Predict the structures of the given clusters with different heteroatoms. There are at least about 20 examples, so try to work out as fast as possible. One example I have given you. Tell me the answer. SB9H13. Is it closer nudo arachno hypho clado? Clado. You're doing arachno. Arachno. So how did you get it as arachno? Sulfur is, you are counting it as a 6 electron system. In the Hoffman isolable analogy, we have given which particular unit is isolable to what. In that, we have given a CH3, CH2, CHC, and so on. A CH2 is a 4 plus 2 6 electron system. That is isolable to some units. And finally, we have given oxygen, sulfur, selenium, and tellurium. Polonium is excluded from that. Okay. So a sulfur is taken as a 6 electron system. A 6 electron system means, can I take it as a BS3? Because everything, if I put it into Borane terms, it will be easy for me to calculate. So a sulfur is a 6 electron system. BS3 is a 6 electron system. 1 boron and 3 hydrogen, 6 electrons. BS3 and B9H13. So what does it become? B9 plus 1 boron is B10. 13 plus 3 is 16. So what structure is it? Arachno. B10H16, as we have done in our previous classes. Just try to find out the difference and put it into pairs. That will give you the answer. B10H16 is arachno. So this structure has arachno. Okay. Next one, C2B7H11COCP. C2B7, it is carbon C2B7H11 COCP. CP refers to cyclopentadienyl. You have to count it as 5 electron system. Cyclopentadienyl is counted as 5 electron system. C2B7H11 COCP. Nido. How is it nido? Let us just calculate. COCP means 9 plus 5. It is a 14 electron system. 14 electron system means it is equivalent to 4 electron system. 4 electron system means BH. A COCP, it is a 14 electron system. How is it 14 electron? Cobalt is 9 electrons. Cyclopentadienyl is taken as a 5 electron system. 9 plus 5 is 14. 14 is isoelectronic with 4 electron. 4 electron is a BH. So I am just equating COCP to a BH. Next, carbon. 4 electron system. Each carbon is a 4 electron system. So in the place of carbon, I can just replace it by BH taken twice. B7H11. Altogether, how many borons? 7, 8, 9, 10. So it is B10. How many hydrogens? 11, 12, 13, 14. It is nido. Okay? It is nido. Suppose they may give you this question if they ask you how many skeletal electron pairs are present. How many skeletal electron pairs are present? When you say nido, what series is it? Nido means n plus 2. So this is nido means n plus 2. How many n? 10. 10 plus 2 is 12. Number of skeletal electron pairs are 12 skeletal electron pairs. Because it is n plus 2, 10 plus 2. Okay. C B10H14. C B10H14. Nido. It is also nido because one carbon is equivalent to BH. So C B10H14 carbon is equivalent to a BH. B10H14. Altogether there are 11, 15. So this is a n plus 2 nido. Are you doing with my factor, anyone? You can follow the factor also. According to the factor, for sulfur, what is the electron? For sulfur, what is electron count? 3. For sulfur, what is electron count? From the factor that I have given you. I have given for carbon. I have given for nitrogen. For oxygen, I did not give. Okay, oxygen I did not give. You just take it as 2. For oxygen group, the factor is 2. Okay? For oxygen, sulfur, selenium, tellurium, the factor is 2. Now can you do it with the factor? N plus. So that is very, very easy with the factor. Next, with the factor. Next, COCP. It is a 14 electron system. Anyway, you have to convert. 14 is equivalent to 4. 4 is 0. Did you get the point? Everyone. 14 is equivalent to 4. 4 is equal to 0. Okay. So, if at all they are giving you a 14 electron system, that does not change your cluster. That does not change your structure. You have to check only for the borane. Did you get the point? What is the B7H11 structure? Nido. COCP is a 14 electron system that does not change. Carbon does not change. Therefore, the structure still remain nido. Okay. Wherever you get carbon and its equivalent, it will not change the structure of your cluster because the factor is 0. Right. Next for this, C-B10H14. Nido, because carbon is 0. Nido structure. Next, C2B9H11. You try to be as fast as possible so that we can save time. C2B9H11. RuCO3. Closer. Now I'll ask from one bench so that I'll know how many of you are working out. From the last two rows, if you are not able to calculate with the help of the factor that I have given you, try to convert it into a borane. Try to convert it into a borane and then tell me. Whatever factor that I have given you, that is a logical factor that will give you answer within seconds. Okay? But if you are not able to do, then simply what you do is, ruthenium is 8 plus 6, 14. 14 means it is a BH unit. 2 carbons means 2 BH units. And this is B9H11. So altogether how many borons? 9, 10, 12. How many hydrogens? 11, 12, 14. So it is a closed structure. B12H14, it is a closed structure. Each carbon is equivalent to a BH. 2 such carbons, 2 BH. RuCO3 is a 14 electron system, is equivalent to 4 electron. So it is equivalent to a BH. So altogether it is giving you B12H14, it is a closed structure. Next one. From last row, are you ready? Others please don't answer. SiC2 B4H10. SiC2 B4H10. Carbon, silicon, germanium, tin, lead. Who can answer in 2 seconds? Arachno. It is so easy. Because what is the factor? What is the factor? Directly you are checking for B4H10, it is arachno. Or silicon is a 4 electron system, 2 carbons, so altogether 4, 5, 6, 7, B7, 10, 12, 13, N plus 3 arachno. C2B4H6, NiPPS3 taken twice within 5 seconds. Closer. So in 2 seconds you have given the answer. C2B4H6 NiPPS3 taken twice. How many electron system is this? 14 electron system. 10 plus each triphenyl phosphine is a 2 electron system. So it is a 14 electron system. 14 is equivalent to 4, 4 is equivalent to 0. You just make it as a 0. Wherever you get 4, you make it as 0. It will not affect your structure. Carbon, it is a 4 electron system. 4 electron system is a 0. So even that does not affect your structure. So B4H6, this is what you are finding out. Directly, whenever you are looking at it, you are making this as 0, this as 0. B4H6 is closer. Finished? Next one, PCB9H12. Phosphorus, carbon, B9H12. Nido. It is nido. N plus 2. Are you getting it? Nitrogen is isolable with BH2. Nitrogen means 5 electron system. So this is equivalent to a BH2. This is equivalent to a BH. This is B9H12. Altogether how many borons? 9, 10, 11, 12, 13, 14, 15. It is B11H15. Altogether it is a B11H15, N plus 2. Nido. Or from the factor, what is the factor for this? So you just add this to this. Difference is 3. You are adding that, converting into page, giving the answer. So hardly 4 to 5 seconds. 5 seconds is the maximum time. If you are able to work out with the factor that I have given you, 5 seconds is the maximum time. You need not convert them into boranes. Germanium, carbon, B9H11. So at least 2 seconds you have taken. Now it is becoming easy for you. SB9H11. Nido. Right. NC B10H11. Closo. If anyone is finding difficulty, simply convert nitrogen into a BH2 unit. Nitrogen, phosphorus, arsenic, antimony, bismuth into a BH2 unit. Carbon is a BH unit. Then B10H11. 10, 11, 12, altogether 12 borons. 11, 12, 14, altogether 14 hydrogens. Okay, so it is equivalent to B12H14. Next one, B10H12 PCH3, B10H12 PCH3. In the rhenium cluster, I have told you wherever you get a methyl, it is like a 1 electron donor. Methyl is a 1 electron donor. So you count 1 for that. Nido. 1 electron, 1 pair plus 1 pair, 2 pairs. N plus 2, nido. Finished? Next one. Wherever you get a phenyl, you just take it as 1 electron, phenyl. B10H12 P C6H5 taken twice, whole taken minus. P C6H5 taken twice, whole taken minus. Arachno. So this is B10H12, 1 electron, 2 electrons, 1 electron. Altogether how many excess electrons? 4. 4 plus 2, 6. Convert them into pairs, 3. So N plus 3. You take it as a 1 electron donor. C6H5, CH3, any alkyl, any aryl, you take it as 1 electron donor. You count 1 electron. So those who are finding difficulty, please, you have to practice. Okay, because the others are able to answer in within 5 to 2 seconds. So you have to practice, that is all. You will take maybe 20 to 30 seconds if I give you individually. But please don't take even 20 to 30 seconds. Just you have to complete it in within 5 seconds. Yeah, next one. Just a minute, I'll give you a tricky one. P2B10Cl10. P2B10Cl10. Similarly, there is also P2B10Cl10, As2B4Cl4, for all halogens count 1 electron. Halogens count 1 electron, just like hydrogen, you count 1 electron for halogen. First one is closo. Next one. Yeah, what you are saying is right. Closo. Both are same. Both are closo. Okay. Both belong to closo only. Factor, I have told you for boron. What is the factor? Factor. For hydrogen, 1. For any halide, 1. So you now just put the factor, multiply with that. How many will you get? How many will you get? If you multiply with the factor, how much will you get? 1 into 2 is 2. Minus 1 into 4 is minus 4. 1 into 4 is 4. Closo. Okay. So please practice, practice and practice. I find hardly 5 to 10 students answering fastly within 5 to 10 seconds. I want everyone to answer in a similar time. Write down. In heteroboranes, oxygen heteroborane is very rare. Oxygen heteroborane is very rare. This is one of the examples. This is one of the examples. This is one of the examples. What is its structure? What is its structure? Neta 6, C6, CS3 taken thrice, S3, Fe, 6, O, B8, H10. Now looking at this structure, you need not get confused. In your organometallic chemistry, there is a ligand called as benzene. You are aware of benzene? This forms a ligand in organometallic chemistry. It is a pi-arene system. Okay. For this, what they have given is, if one is hydrogen, one is hydrogen, one is hydrogen, the other three are methyls. That is what they have given. So you need not get confused. Hydrogen, hydrogen, hydrogen. This is methyl, methyl, methyl. This is attached to iron. Iron is attached to further cluster. So what type of unit is this? This is a Neta 6. Neta 6 means 6 electron unit. 6 plus 8, 14 electron system. It is a 14 electron system. 14 is equivalent to 4. 4 is equivalent to 0. Forget about this. Next, B8H10 and oxygen. Nido. This structure is nido. Okay. So for oxygen, what is the factor? You add it to the difference of boron and hydrogen, put it into pairs, that will give you the answer. N plus 2, nido. Now, some rare, did you take down? Neta 6 means count it as 6 electrons. Neta 5, 5 electrons. Neta 4, 4. So whatever they give here, you count it as that electrons. So this is 6 plus 8 iron. 14 electron system. Next one, what is the structure of platinum at Pb12 2 minus? Suppose if you get such a question, how should you proceed? Just like your Gmail @ you find, here they give platinum at Pb12 2 minus. So whenever you get such a cluster, what you have to imagine is, this is a cluster formed by lead, Pb. It is a cluster formed by 12 lead, in which platinum is present. It is just like interstitial. So you have to consider it as interstitial. Don't count any electron from platinum. It is not going to give you for skeleton. Don't count. Make it as 0. You just make it as 0 because platinum is present inside. It is just inside that polyhedra formed by this. Now tell me the structure. N plus 1. So N plus 1 means closo. N plus 1 is closo. Okay. How is it n plus 1? I said platinum you don't consider because it is not participating in the skeleton formation. Whatever skeleton that is being formed, it will just enter into that skeleton. So don't count for this skeletal electron pairs. Now we are left out with lead. Carbon, silicon, germanium, tin, lead. Carbon is equivalent to a BH, 4 electron system. 4 electron system means 0. But how many excess electrons? 2 electrons, 1 pair, n plus 1 closo. Okay. How many lead are there? 12. So what type of structure can you expect? Icosahedra. It is a icosahedra. So write down a point about this. First of all, for such clusters, how you have to proceed, I'll tell you. For the above cluster, the platinum metal, will be present in the center of the polyhedra, formed by lead. Such a platinum does not provide, such a platinum or such a metal, let it be platinum or some other metal, such a metal or platinum does not provide any electron for skeleton formation. Okay. So don't count any electron from platinum, directly go for lead. So what is the structure we have? Icosahedra. In this icosahedra, which is a polyhedra, platinum will go and settle. So platinum will be present in the center. This is the structure of that cluster. Platinum at lead 12 2 minus means this will be the structure formed by lead. In that there is a space inside. In that space will go and settle your platinum. Okay, that is the structure of your cluster. You can just draw that structure. Meanwhile, I'll give you one more question. Next one is nickel at lead 10 2 minus. How many electrons will you count for nickel? You will count 10. 0. Because it does not provide any electron, it will just go and settle into the skeleton formed by closo. It is a closo. So if it is a closo, for 10 central atoms, what will be the geometry? Parent polyhedra I have given you, starting from 4, 5, 6, 7, 8, 9, 10. For 10. For 8, square antiprism. For 6, octahedra. For 7, PBP, pentagonal bipyramidal. For 8, square antiprism. For 9, monocapped square antiprism. For 10, bicapped square antiprism. Okay, tricapped trigonal prism will come for some geometries. But for this, the parent geometry is bicapped square antiprism. So it is a closo structure as you have told. But what is the structure? I mean, what is the geometry? Bicapped square antiprism. This is bicapped square antiprism. And where do nickel go and settle? In the center. In that bicapped square antiprism, nickel will go and settle in the center. So this is the structure of your cluster. Last one. Palladium 2 at germanium 18 4 minus. It is nido. Structure is nido. But giving the geometry is very difficult for this, because it is 18 germanium altogether. It is 18 germanium. Geometry you can simply write it as single deltahedra. Single deltahedra. Single deltahedra means some polyhedra which is having triangular faces. I've told you there will be many polyhedra. Polyhedra can have a triangular, square, pentagonal, hexagonal faces. If any polyhedra has all triangular faces, you call it as a deltahedra. So it is a single deltahedra, a very large structure into which two palladiums will go and settle. Two palladiums will go and settle into that. Okay? Finished? You just try to work out these two. Meanwhile, I'll show you an article. Take it down. SB8 2 plus SB8 2 plus bismuth 8 2 plus. How many skeletal electron pairs are present in it? How many skeletal electron pairs? SB8 2 plus and bismuth 8 2 plus. Now just look once. Here there is a research article. So palladium 2 at tin 18 2 minus or 4 minus. Previously we had, it was germanium. Germanium, carbon, silicon, germanium, tin, lead. It will have some similar structures. How will be the structures? I'll just show you. Now previously we have seen one structure where we had icosahedra. Where we had an icosahedra. So if the lead is forming an icosahedra, into that the palladium or platinum will go and settle. This is how it will go and settle into this icosahedra. So this will be the skeleton made by germanium or tin or lead, into which the metal will go and settle. Platinum, palladium, nickel and so on. This is one more such cluster. What type of structure geometry is this? What geometry is this? Can you say this? One square and cap, one square and a cap. Bicapped square antiprism. Previously, whatever bicapped square antiprism I have given you, so this is how it will settle. Icosahedra. Okay. Now for the last one, we have given single deltahedra. Structure will be very large, into which two metal atoms will go and settle. This is that structure. All this is a single deltahedra. So here they are tin. Whatever blue color that are present, all these are tin. In the place of tin, you will be having germanium. This will form such a large deltahedra, into which palladium and palladium will go and settle. So it is very difficult to tell the structure also. I cannot call it as icosahedra, I cannot call it as something else. It is a simple deltahedra. Deltahedra means whatever face that I see, it is a triangular face. Triangular face. So wherever you see, it will be a triangular face. That is called as a deltahedra. Sometimes what can happen is, two polyhedra may come and fuse. We have discussed in the clusters. Either they may fuse with a vertex or a edge or a face. There is one such structure. See, here it is. Again the same deltahedra. It is a single deltahedra where the two metals are present. Or it could be like, this is one structure where one metal will enter, another structure, another metal will enter, both polyhedra will fuse with a vertex. This structure was defined as a single deltahedra. It is a single deltahedra. This is not a single deltahedra. It is multiple. Two polyhedra are joining with a common vertex. Okay? So this is how the structures will be for the clusters. Right, so with this we'll close. We have octahedral halide clusters to discuss.